So we'll begin today by looking at this question from the homework. It's number 7, 4x plus 3 squared plus 2 equals 22. So let's give this one a shot. First thing I think of when I see this equation is, okay, maybe I can get it into what we're calling standard form, which is ax squared plus bx plus c equals 0. And the first part of this problem is to do all the work required to make it look like that. So the first thing we need to do is actually FOIL out this 4x plus 3 squared. It is tempting, but wrong, to say that this is equal to 16x squared plus 9. It's very tempting. Square the first thing, square the second thing, and it's just not true. So let's not do that. Whenever I see something like this squared, I write it twice. 4x plus 3, 4x plus 3. I'll copy everything else. And as soon as I've written it twice, which is what squared means, I recognize, oh, this is the FOIL or this is the lobster claw, but it's definitely not just square both terms separately and then stop. So we FOIL here, 4x times 4x is 16x squared plus the outers, 12x, plus the inners, 12x, plus the lasts, 9. So the 16x squared plus 9 is the tempting answer, but you completely miss the outer and inner stuff. And you're not going to get the right answer. I'll just copy the other terms here. So we're just going to underline this thing, expand it out to become that thing. Any questions on that so far? And the reason we knew we had to do something like that is that there's no room in our blue standard form for parentheses. We just can't have it. So you got to do what you need to do to get rid of those parentheses. Okay, so it's almost in standard form. We want to get one side equal to 0. So let's combine over here 16x squared plus how many x's? 24x plus over here 11 is 22. It's very close to blue. What's the only difference? We need 0. So subtract that 22 from both sides. And now that it's in standard form, we're ready to write down the values of a, b, and c. A is in front of the x squared. What is it? 16. B is in front of the x. It's 24. C is the other term. C is 11. C is negative 11. And at this point, we start to use the most complicated formula we will see at any point this semester. The most complicated formula we will see. Did you find out if having a little piece of paper had that form on? Good question. So Michelle had asked last time if you could bring in a little card that walks you through the 6-step process for drawing a parabola. You know, like, is it up or down? Find the y-intercept, find the x-intercepts. So good news and bad news. The bad news is no. The good news is on the question on the quest where I say draw the parabola, I will walk you through. First, find if it's up or down. Next, tell me what the x-intercept is. So it's in the quest itself. I don't know. Yeah, but it's there, so you don't even have to worry about it. You just follow the step-by-step process. Okay, that was that. One other question that came up about the quest, somebody had asked, would there be any word problems? Because there have been some word problems sprinkled through the recent homework assignments. And to be honest, some of the recent homework assignments I've assigned some questions that I didn't realize I had assigned, and they weren't quite appropriate for what we had covered at that point. There won't be any word problems on the quest. We are going to do word problems today. That's the new material for today, but today's material is not on the quest. All right. Okay. So let's, Glenn, is that enough? I mean, then it's just a matter of plugging in and you get what you get. ... Any questions on this one? Okay, so then one other thing to say about the quest is once again, you've got the sample quest problems starting on page 56. If you do no other work in terms of preparing for the quest, at the very least, answer the questions on page 56 and the next page. Any problems that you cannot do is a big warning flag, and you need to get those problems answered before Friday. Okay? So Friday is our quest. Answer key is here. There are also videos of me going through each of these problems on YouTube, so that's a great resource if you get the wrong answer for any of those problems. And in terms of starting the quest early, we can do the same kind of thing we've been doing in the past. So the quest on Friday, you can come early at 12:30 and you can stay late until 2:30, just like before. Still written to be an hour and 10 minutes, but I want people to not feel rushed or pressured, so start early, come early if you are worried about time. Evan.
I was just quickly looking at the practice problems for the quest.
Yes.
There's supposed to be a number before this.
There is. Which question is that?
Number 4, letter A.
Thank you. Yeah, there's a hole punch through this 4 in front of 4A. So on the top of page 57?
Yes.
Should be a 4x squared minus 100. There's a hole punch through the 4. Four x squared. Okay, any other questions about the quest before we do the new material, which is not on the quest? Okay, then we're going to go back down to the bottom of page 57. And we're going to do this height of a baseball activity. So we'll begin with the formula. Can we start here with Ben? I'm just going to read this part.
The formula for the height of the baseball comes here. H equals 16t squared plus 64t plus 4. H is the baseball stay in feet. T is the time in seconds.
Okay, so there's a crazy formula there. H is the height, T is the amount of time since it's been thrown. So we've all seen a baseball thrown, so we have a sense of what it looks like. What does it look like? It kind of looks like a parabola, right? You throw it, goes up, goes down until it hits the ground. So let's see what this formula tells us. So how about we're going to fill in some numbers in this table. So if we plug 0 in for all of the t's, that's a 0, that's a 0. If I see that the first parts are just nothing and we just get the 4. So plugging 0 in is easy, we get 4. Plugging these other numbers in is going to be a little bit tougher. Let's try plugging in, let's plug in the 3. So I'd encourage you guys to write this down. Even if you're going to use your calculator, I would encourage you to write this kind of thing. Negative 16 times 3 squared plus 64 times 3 plus 4. That's changing all of the t's to 3's. Teresa? What do you want to do? Divide everything by 4. You could factor this guy. You can pull a 4 out, but it's still going to be there. It doesn't just, you can't just divide everything by 4. You can factor out the 4. Maybe the same. It's 4, 16t plus 1. Yeah, so the numbers in there get smaller, which is good, and then you multiply by 4 once at the end. It's okay. All right, and so we'll do this calculation, and I'd do as much as I could without the calculator before I started punching buttons. Are you supposed to do 16 times 3 or 3 squared first? 3 squared, so that's really negative 16 times 9, right? And then plus 64 times 3 plus 4. And at that point, I would feel comfortable typing that into the calculator in one shot. Anybody have a final number for us on this one? 52? 152 sounds too big. Katrina, what'd you get? When you plug 3 in, what do we get for that whole thing? 52? Yep. Michelle, that's what you got? Great. All right, so that's 52. And we're just going to save a little time and fill in the rest of the chart right now, but everybody's okay understanding how to fill in the chart? Any questions on that? Okay, Katrina, one more time, what's the chart? Okay. Okay, so we've got these 5 different points. What I want you guys to do right now is plot each of those points on the graph paper here. The T is the horizontal, maybe I should have labeled the axes here. T is the horizontal axis, H is the vertical axis. So the first point is 0, 4. 0, 4, and you just ballpark it. So we plot our 5 points and then connect the dots with a smooth curve. Any questions? Smoothish. Near what? Smooth. Yes, it is. It is. Okay, so let me be clear about what this parabola represents. It seems like maybe it represents the path of the baseball. It doesn't. This parabola represents an input is time, and the output is the height above the ground. So forget throwing a baseball to a friend where the path looks like a parabola. Throw the baseball to yourself straight up and then straight back down. And this thing represents how high the baseball is at any moment in time. So it's not moving left or right at all. It's just going straight up and coming straight down. 0 seconds into the experiment, the baseball's 4 feet off the ground. That means when we start, it's just right here in my hand. Then I throw it up. 1 second into its journey, it's 52 feet in the ground, up in the air, I mean. 2 seconds in, it's 68 feet off the ground. 3 seconds in, it's 52, it's coming back down. 4 seconds in, it's 4 feet off the ground, so if my hand were still there, I'd catch it 4 seconds later. But if I move my hand out of the way, it would hit the ground just a few moments after that, okay? So this looks like the path of the baseball, it's not. The ball is going straight up and down. The horizontal axis is time, okay? All right, so let's move to the next page. And in number 3, it asks us to fill in the coordinates of the highest point. So what's the first coordinate? 2, and the second? 68. If that's the highest point of a parabola, it has a special name. Vertex. Vertex. Okay, fill in the 2 blanks. The baseball reaches its maximum height at blank seconds. The maximum height of the baseball is blank feet. Make sure you put the right number in the right line. When does the ball reach its maximum height? 2 seconds in. What is that maximum height? 68 feet. Everybody clear on those 2 numbers? Okay, let's jump down to part 6. Melanie. Okay, let's go back to the picture. I want to find 2 moments in time when the ball is at a height of 64 feet. So if I'm talking about feet, which axis are we looking at, the horizontal or the vertical? It's the vertical. So you go up to 64, again, just estimating where 64 is. And then what do I do from there to find a when? I just go straight across. So straight across at 64. And how many times does it appear the ball's at 64 feet? It's twice, 2 places where we meet. And again, we're just going to estimate this number. So I'm looking here maybe, and here maybe. To me, it looks, and then you go straight down to find the time. That's what it looks like to me. Right around 1.5 seconds in and 2.5 seconds in. If you put 1.4 or 1.6, it's okay. So those are our 2 answers to this question. Let's see, use the formula. All right, so we're down here in 6. The baseball will reach a height of 64 feet at times t equals 1.5 seconds and 2.5 seconds, roughly. Okay, can you guys play the same game in number 7, Glenn? Okay, so this time you want the height of the ball to be 20 feet. So find 20, and then find the 2 points on the curve that look like they are right around the height of 20. Okay, so estimates here. 0.25 seems good. 3.75 seems good. The way my graph looks, it's closer to 3.6 for me, but that's not any better than your graph. It's just the way that I drew it. So 0.25 and 3.75. Are you up for reading 8? We do number 8, Septap. Okay, so we estimated 0.25 and we estimated 3.75, but couldn't we figure out what the heights are at 0.25 seconds? And it's just like when we filled in the table. So very carefully, can some of you put 0.25 in for the t's and some other people put 3.75? So maybe some of you will do this kind of thing. -16 times 0.25 squared plus 64 times 0.25 plus 4. Very carefully plugging in 0.25 for the t's. How much? 20.64? Is that what you said? Yeah. And if we plug in 3.75, I'm guessing we're going to get the same thing. $21. Okay, and I'm going to guess we'll get that for the second one. Did anybody plug 3.75 in? So we'll just give you a sneak peek. If you end up continuing on in algebra here at GCC, the next math class you'll take is Math 107, which is college algebra. You'll end up using a calculator probably that looks quite a bit like this. Without getting into the details, I'm just going to type in that formula, the negative 16t squared. This calculator doesn't use t, it uses x, plus 64t, 64x, and then plus 4. And then the really nice thing is once you type that in once, you can set things up in such a way that you can ask the calculator, okay, I want to plug in t equals 0.25, just do it for me. And you got 21, Tenzin? Anybody get 19? Good. We're going to change that. 19. All right. So you can plug that in and it'll just spit out the answer, or you can say plug in 3.75 and it'll just spit out the answer. And again, we get the 19. And we could have made the whole chart using this. I could just say, okay, 0 and 1 and 2. See the numbers that we've seen before? Right. So the technology is there to make it so you can fill in a chart very easily. Yeah, Evan. That is not a question I'm going to answer on record here. Yeah, good. Okay, let's move on to I'm moving on here, number 9. Oh, okay, so sorry, 19, is that what we were wanting? What height did we want? We wanted 20. The fact that we got 19 is just because the right answer wasn't exactly 0.25, but it's something very close to that. And getting as close as we got with a 19 instead of a 20 is good enough. I mean, we were relying on our graph. Okay, so here's what I'd like to do. Let's move on to number 9 here, and we're around to Tenzin. Okay, so forget the fact that we estimated our answers at 1.5 and 2.5. We're just going to try to answer this question completely separate from how we did before. We're not going to rely on the graph at all because we know that that gives us only approximations. So I want to know when the height will be 64. Is the height a t value or an h value? An h value. So what we're going to do is replace all the h's, there's only one, with 64. So I'm going to copy that whole equation again, making only that slight change that the h is 64. And now it's a regular old looking quadratic equation. And what number do we always like on one side of the quadratic equation? 0. So let's move that. So you can either move the 64 to the right, or you can move all 3 of the other terms to the left. And I had said at one point that if there's a negative in front of my x squared, then I always move it to the other side to make it positive. If I'm going to use the quadratic formula, and I'm certain I'm going to use the quadratic formula here, it makes no difference to me if it's a negative in front of the x squared. So why don't we just leave it, because it's easier only to move the 64 over. So subtract 64 from both sides. And 4 minus the 64 is negative 60. And then we would use the quadratic formula. Now, I want us to save a little bit of time. I don't want to sit here while we all do the quadratic formula because I trust that you had enough practice with it last night. I mean, this is just another example of using the quadratic formula. So I'll say this, use the quadratic formula and don't be surprised when you get t is equal to 1.5 and t is equal to 2.5, right? It's going to come out when you do the quadratic formula, you'll get those two numbers. The fact that those are nice numbers, what kind of thing must the discriminant have been? Those are two rational numbers right there. But it must be a perfect square. So when you do that discriminant, you're going to get a perfect square. What is it? 256 is underneath that square root. And the square root of 256, you'll find up here in yellow, 16. which is how we're going to get nice numbers, because normally the quadratic formula gives you very messy decimals. All right, number 10, Teresa. Okay, so if the ball is hitting the ground, then how high off the ground is it? It is 0 feet off the ground. And is that 0 a T or an H? It's an H. So all you're going to do is put a 0 right there. Everything else is the same. And then you do the same exact thing. Yeah, and you're going to solve this, and you're going to get T equals some number, and that number is going to represent when it hits the ground. So because we don't know the answers to this, I'm going to ask for the answers here on Wolfram Alpha. So again, it's a quadratic formula. I'm not going to go through the details, but let's just jump to the answer, because the answer might be a little surprising. So what was it? It was 0 equals negative 16 t squared plus 64 t plus 4. Oh, come on. 0 equals. So the quadratic formula is going to give you how many answers? 2. Almost all the time it gives you 2, which is kind of weird, because how many times does the ball hit the ground? Just the once, and then it'll bounce, and our formula will break down as soon as it starts bouncing. But we're going to get 2 numbers. They're not going to be very nice. There they are. Here are the 2 numbers. Not at all a surprise that you have some number minus and then a radical, and then down here some number and then plus and then a radical. Here are the 2 decimals. One of them makes quite a bit of sense to me, just looking at the picture we drew. Ballpark, when does the ball hit the ground? Right around 4 seconds. That's where it looks like it hits the t-axis, the horizontal axis. So I'm not at all surprised that 4.06 is one of the answers. I am surprised by this, because what kind of a number is it? It's negative, which doesn't make any kind of sense, because t is time and time isn't negative. Well, yeah, the math doesn't understand that there's a baseball happening and negative time doesn't make sense. All the math is doing is finding when this parabola hits the horizontal axis. And it certainly hits over here at 4.06. If the parabola had continued, then do you buy that it would have hit someplace very close to 0, some slightly negative number? And in fact, it would have hit at exactly this slightly negative number.
Would it be fair to say that that negative number kind of represents the act of the ball?
It is a before the experiment began, but I don't want to say it represented picking up the ball. What it represents is if instead of throwing the ball from 4 feet, you had let it drop the rest of the way, or if it had been fired from the ground and then it would have passed through your hand at 0 seconds, it would have been fired at minus 0.06 seconds.
Okay.
Yeah. So I show that just because I want you to know what to do when you get 2 answers, one of which is clearly doesn't make sense in the context of the problem. Okay, so then we'll put our 2 answers here. We said one of them was, so this is the quadratic formula. One of them was minus 0.06, and the other one was 4.06. And this one here we are going to reject. It just doesn't make sense. Okay, let's take a look at on the next page. We're going to skip a couple of these problems. I want to get to number 14 here. So 14 will go over to Evan.
How big a piece of cardboard is?
Okay, so let's do a quick visual here. So we've got our piece of paper. It's supposed to be square. I've got a rectangle in front of me, but that's okay. What we're going to do is we're going to take the 4 corners. We're going to rip them off, little squares from each corner, the same size from each corner. And then when we do that, we're going to just get a flat piece of paper with the squares, with the corners missing. So what we're going to do here is we're going to make a 3-dimensional box with no top by folding up each of the sides right across where the squares used to be, the cutouts used to be. And so if we do that, we get this wonderful object right here. A box with no top, yes? That is what's represented by this right-hand picture over here. My box without a top. And it just came from a piece of paper, cut out the sides, fold it up. Now, I chose to cut out sides that were roughly this long, however long that thing is. Suppose that this was a really small square that I had cut out. What could you say about the height of the box that I would get? It would be really tiny. Could you imagine like a really wide box here, but just a little tiny height coming off it, like a drain pan for like draining your oil out of the car, right? Like one of those. Yeah, like a really, really thin food tray, because you'd only be cutting out this little tiny stuff. And so I'd only be able to fold up just like a little bit instead of folding up this entire thing. I'd only have like that little thing folded. So it'd be quite big in its base, but very, very small. What if I went even more extreme? What if I cut more stuff out of here, just made like the squares a little bigger? What would happen to the height of my box? It would get taller, but you'd pay for it because you'd be losing some of the base, right? And so the volume that you get, like this thing right here holds some water, not very well, but it holds some volume. And if I had instead cut out smaller squares, I would hold a different volume. It would be this long, very short pan. Or I could cut out a lot of stuff and make a really tall thing, which again would hold a different volume than this one does. So the condition here is that you want to cut the squares out. You're trying to figure out how much stuff you need originally, so that when you cut out those 4-inch squares, the space inside of this thing is exactly 100 cubic inches. I want to cut it so that it's exactly holding 100 cubic inches. So let's give this a shot. The unknown in this problem is how big a piece of cardboard is needed. So how about we introduce a variable? Let's say x is the length of one of the sides of the piece of cardboard. So we're going to call x that distance. And the piece of cardboard is supposed to be a square to start with, which means that x is also the other distance. Okay? So let's see what we have. So what math word describes this 100 cubic inches? Area? It's a volume, right? That 100 cubic inches is a volume. So clearly we're going to need a volume formula, volume for a box. In English, does anybody know how to find the volume of a shoebox? That's it. Length times width times height. Yeah? Okay. So I'm going to write L times W times H. Length times width times height. So what we need to do is figure out what those things are in terms of the x that we start with. So let's come back to my lovely piece of paper here. Okay, suppose, all right, so the length is this distance right along here, right? That's the length. So the length is this thing right here. The width is this thing here. The height is that thing there, right? Okay, so let's just focus on this one edge of my cutout here. The length is this guy. Let's flatten it back out. It used to be a certain amount long, right? I don't know how long it was. Then I took away one square here, and I took away one square here, and whatever is left is the length of the new box, yes? So how long, we gave a name to it, how long was the entire thing to start with? Was x. So then the distance from here to here, let's see, it used to be x, it was the whole thing, but then we cut out some stuff. How much did we cut out on this side? We cut out 4 inches. And how much did we cut out on that side? Another 4. So minus 8 is, x minus 8 is the length of the shoebox. Melanie says it's also the width. How come? Yeah, we started with the square, so it's exactly the same. So the width is also x minus 8. The piece of cardboard we started with was a square. We will write that. We will get there. Yeah, you could say it. And what is the height of the box? Yeah, it's given in the diagram. It's 4 inches, which hopefully makes sense because 4 is how much you cut out. And so 4 is the same as this. And when you fold it up, that becomes one of the heights, right? So the height is 4. So let's start filling in. We decided that the length was how much? X minus 8. The width was also x minus 8. And the height is 4. Perfect. And then here's the last piece of this puzzle. This represents the volume. And I know what I want the volume to be. It's given. What do I want? I want it to be 100. So equals 100. Yeah, that right there, if we rewrite it, is going to be a standard looking quadratic equation. And we can solve those. Yeah, we're going to have to FOIL. There is a 4 right here, which you're welcome to send in to the parentheses. But to be honest, our lives will be easier if we first divide by 4. So let's be smart about this. I'm going to divide both sides by 4, right? As long as you do it to one side. When you do it to the other, you're okay. 100 over 4, 25, equals x minus 8, x plus, another x minus 8. And what happens to these 4s? They just cancel. Yeah, it's a good question, and I'm glad you asked. So when we have examples like this, 2 plus 4 square root of 15 all divided by 2, then we know we're supposed to split this into 2 fractions, right? So this is equal to 2 over 2 plus 4 root 15 over 2, yeah? And then you can reduce both of those fractions separately, which means the single 2 in the bottom actually ends up underneath both on top, right? Which looks quite a bit like what we have here. But the difference is that the main operation in that is what? It's addition. And the main operation over here in blue is multiplication. And that is a fundamental difference. For addition, you guys know that when you add 2 fractions, 5/3, if they have the same denominator, what do you get to do? You just add them on top. I'm not going to write 7. I'm just going to write it as 2 plus 5, right? That's the property that says you're allowed to split it up into 2 fractions. It's just going the other direction. But when you're multiplying things together, A times B times C, and then divided by C, it just straight cancels. I mean, there's no addition to split things up into. If you tried to split it up, say, for example, you decided, oh, it's really A over C times B over C times C over C, right? Like following that kind of pattern. How do you multiply fractions? You go straight across. What do you get upstairs? ABC. That looks good because that's what we started with. ABC. What do you get downstairs when you multiply? You get C cubed. It doesn't look good at all. So you can't split that C up and give me 3 fractions because then you're kind of saying, oh, I have C cubed down there. You don't. You don't know if that helps, but that's the difference. Multiplication, it doesn't split because that's not how multiplication works. For multiplication of fractions, you multiply straight across. Okay, so then we have this black equation that I think we're ready to continue solving. This one here, 25 equals, is this true or false? X squared plus 64. X squared, no? You don't get to just, all right, you got me. Minus. True or false? Still false. Just seeing if you're paying attention. That's it right there. What do you need to do before we use quadratic formula? Okay, so 0 on one side. 64, 25, thank you. And now it's in standard form, so we can use the quadratic formula. The fact is, if it factors, then that's probably a better option than the quadratic formula, and this one does. I wouldn't spend very much time factoring, but 39, there's only a couple of numbers that make 39, so I would just check real quick. What numbers go into 39? 3 times 13, right, so and 3 and 13 add up to 16. So you can use the quadratic formula. We're just going to skip to the factored version because it's faster. Without all the details, thinking of a product of 39 and a sum of negative 16. And the two numbers are? Good. Yeah, so I'll write this step out, set them both equal to 0. So that's it. What does it mean? It means if my piece of paper that I ripped up here had been 13 by 13 inches, and I cut out little squares of 4 on a side, and I fold it up, what will the volume be? Exactly 100. Same kind of thing if x is equal to 3 inches, if the whole thing is 3 on a side, and then we cut out 4s. Anybody else troubled by that? What's the problem with x equals 3? Yeah, we would have negative numbers here, right? I mean, look at what you're cutting out. You're cutting squares of 4 inches out. So a 13 is okay. I can cut out 4s from a 13. I can't cut out 4s from a 3. So even though x equals 3 seems like a perfectly reasonable number, it needs to be rejected. It doesn't make sense in the scope of the problem. So let's look at the x equals 3 real quick. So suppose that we plugged x equals 3 into our formula. See this x minus 8? How much is that when x is 3? It's negative 5. So that would mean one of the sides of my box would be negative 5. What about this side? Also negative 5. And then the height is still 4. And what do you get when you find the volume of my box? It's still 100. Doesn't mean anything. It's just that, so negative 5 is a length, doesn't mean anything, but somehow negative 5 as a width will cancel out the negative 5 length, and you get 100. Good question. It's rejected because even though it solves the equation, it does not solve the problem. The problem says find me the lengths of the piece of paper or the piece of cardboard to cut out, and x equals 3. I would really hope that you will pause and make sure they both make sense and recognize that 3 doesn't work. I would like to see the word reject on, yeah, that the word reject is not worth half the points of this problem. The word reject is worth 1 point on this problem. So like, don't get all flustered. Oh shoot, I'm not going to know to reject it. Just know that at the end of each of these word problems, you're supposed to pause and make sure that the answers make sense. Quadratic formula will always give you 2 answers. Sometimes they both make sense, but sometimes only one does. All right, if you go to the next page, you will find the group activity, dimensions of a garden, and then there's another problem here with the ball, but let's see if we can get the first 2 done in the next 20 minutes.